Well, hello friends. Today we are going to work a little bit on the kernel. And, oh, I'm still building here. So the thing I have in mind today is a little bit of scheduler refactoring. And I would like to, so currently the way the scheduler works is that all the threads are just in one big list together. It's called like G threads, and a global thread list. And I'll show it to you. It's oh god, where is it? Here. It's just an inline linked list of threads. And an inline linked list is one of my data structures that implements a linked list, and then the objects themselves are responsible for keeping next and previous pointers. So that's just what that is. And I would like this to be broken up into multiple lists or queues, if you will, because currently the way the scheduler loop looks, whenever we look for something new to do in the scheduler, we have to iterate over the entire thread list. First, we do this unblocking pass here where we go through all the threads and check if any of their block or wait conditions have been satisfied, and then they become unblocked. And then this is for dead processes, but ignore that for now. But here we look through all the thread list again to see if there's anyone with a pending signal. And then we look through all the thread list one more time to find who to run next. And all of this happens every time that we hit the scheduler. So it's very, very many times per second. And I would like, it's not currently a performance problem, but it's the kind of thing where I would like to improve on the design now while the code is still small, because it's so much easier. So what I would like to do today is to break this thread list into two lists, one for blocked threads and one for runnable threads. Or basically one for runnable threads and one for everything else. So that when we choose which candidate to schedule, then we only have to look at the ones that are runnable. And also when we do the unblocking pass, where we look at everyone's block conditions, then we only have to look at the ones who are not runnable. So, you know, cutting out a fair amount of work there. I guess we can just get right into that. So then let's start with G threads. And where was that? Here is the declaration and here's the definition. Okay. So I imagine that it's still useful to have a place where you can find all of the threads. So let's make a hash table of all the threads. And it can just be like a hash table thread. Call it all threads. And it would just be static hash table, blah, blah, blah. Table. If no table, then table is new this. Okay. I don't have to do this because I don't have a way of running boot time or startup time constructors in the kernel right now. Maybe one day I will, but right now I don't. So I have to do this little dance here to be able to have a static variable, static global like this. So in the thread constructor, actually let's assert that interrupts are disabled in this thing, because this thing is going to be, you can only access this thing when interrupts are disabled, otherwise it's going to be a huge mess. So let's just put that here as well. I'll just maybe at the bottom. No, not extern, but like that. Right. Okay. So the way the thread constructor currently works is that at the very bottom, unless this is for PID0, which is the kernel process or the idle process, unless it's for that one, then we prepend it to the big thread list. and the kernel process is special, so we don't put him in the thread list because we don't ever need to evaluate him in the scheduler anyway. But what we're going to do here now instead is that while we have interrupts disabled, we are going to do all threads, set this. Oh god, all threads is something else. All threads. Oh, it's a helper that does this. Okay. We'll just call it thread table. Or all exists all live threads. All live threads. Is that cool? But we could have dead threads. They would still be objects. I don't like this clash. Let's just call it thread table then. Be that way. Threads. Thread table. Fine. Whatever. So we are gonna put it in the thread table. And then we will, instead of adding it to G threads, we will add it to where exactly? What exactly is your state when you are started? State is invalid. Okay. So that's gonna have to go in the non-runnable list then. So let's make two lists. We'll call them non-runnable threads and G runnable threads. Okay. And then in thread.h, we gotta rename those that. We'll rename him to runnable threads and non-runnable threads. Okay. And for each in state, that's gonna have to go through them for auto thread in. Wait, what am I thinking? Oh, we gotta make these things work here. Okay. So I guess what we could do in these helpers is that we could just make two loops that iterate over each of the lists. But I'm thinking, could we do something differently? We use all these, yeah. We could also just iterate over the hash table. So for each in state, if state or state runnable, then auto, let's see, we should pick which list to look in. So no, then list is thread list. In that case, it's runnable threads. Otherwise, that would be non-runnable threads. Okay, thread list. And we just start like that. So for this, that would work. And for these, for each living, it's less obvious where to look. So, and same thing for each, we just need to do everyone. So for these, the ideal thing would be to iterate over the hash table, but the problem is that the hash table doesn't have this kind of next iteration that would keep working correctly if we mutate the thread list in here. So course, this thing here isn't exactly super foolproof for that either. But let's just start with something here. So the easiest way to make progress is to just do this. Then we can come back to this. Okay. We'll see if it works. So obviously it doesn't work. So let's go and look for G threads everywhere. So in process for each thread, we look through all of the threads. And I guess we can just do the same thing here. This is not fancy, but it will work. G threads. Scheduler choices. So this guy just needs to look at the runnable threads. And same thing here. Only runnable threads are interesting. And here we only want to look at the non-runnable threads. So let's make a loop for that. So auto thread G non-runnable threads head G okay. Oh, right, but then when we unblock, they're going to move to the other list, so we can't do exactly this. Did we already take care of this in for each, actually? For each. Yeah, so we're already doing this thing, so let's just do that. And we can say thread putter. Thread is thread putter. Say thread next. Not modified in loop body. Right, but I'm going to. Oh god, there's so many continues. Oh, right, because this used to be, okay, this is just horrendous to do this way, so let's fix up the helper instead, and we'll do for each runnable. That's what I wanted in the first place anyway, so I don't know what I was thinking. Okay, for each. So we'll do for each runnable, and that would just be that. Guess this could just be, we could just do that here. And we also want for each non-runnable, because that's the thing that I actually wanted to use in the other piece of code. For each non-runnable. Okay. Let's start with this, and we can tidy it up later. So for unblock, we want for each non-runnable. Okay. And what unblock is going to do now, oh, let me tell creator that I'm in the kernel, actually, okay. So here we want the, to remove from the thread table, and oh, interesting, what if inline linked list remove, What if you remove something from a list that it's not in? Remove. That's curious. I mean, it's not runnable when it's here, so it's definitely in the non-runnable list. Or if it would be in the runnable list, then we would be making a mistake by being in the destructor. So okay. So then what unblock is going to do is that it's going to move the thread from the runnable list to the from the non-runnable to the runnable list. And that would be if current is this, I have to stay running. That's fine. Let's say is let's see. So let me unconfuse myself. Okay. G runnable threads append. G non-runnable threads remove this. Okay. And for block, it should be the other way around, that we move ourselves from the from this thread to from the runnable to the non-runnable. So after set state, then we will do runnable remove, non-runnable append. Probably we have more G threads, yeah. Right, so here we wanted non-runnable threads in the constructor. G threads, but not dying threads. Oh, most of these are dying threads. Okay, so all threads, all it needs to do is for auto get thread table threads append thread, and we can even be nice and ensure capacity thread table that size, because we know exactly how big it is, so we don't even have to check. Actually, unchecked append, which is a vector append that doesn't verify that there's space, because we know here that we made enough space. And oh yeah, and this actually becomes slightly nicer now, because we can just do thread table contains like that. We don't have to iterate. So just this guy left, huh? Runnable threads and non-runnable threads. Now, will this work? I feel like I probably made at least 10 stupid mistakes here, but let's see where we get to. Okay, so we are crashing on startup. That's great. Let's add some scheduler debugging output so we can see what's happening. Okay, so how far do we get? Scheduler choices. And then we crash when we try to look at the choices. Well, that's pretty bad. Didn't I instantiate this thing? Runnable threads, non-runnable threads. Set state. So I'm thinking we should probably let set state be the place where these things happen. So let's move that out of line. And let's say thread set state, new state. Okay. If new state, and then we can do something like is runnable state. Return state is thread state running or thread state runnable. Static bool. Okay. If it's a runnable state, and let's see if it's runnable state. New state. So let's say that we call that one old state, new state. M state is new state, and then if the old state and so if we are going from non-runnable to runnable, then we do the other thing. Okay, so then we have that, and then we also have, if it was runnable and it becomes non-runnable, then we do this. Okay. What was wrong with that? Oh, no semicolon. I'm sorry. Okay, so there's probably all kinds of ways to implement this type of thing that has been written about, but I've never read about it, so I'm just sort of playing by ear now, and we'll see if this makes sense. That didn't work either. So let's look in the thread constructor. Who calls new thread? That would be probably here when we create the main thread for a function. The new thread, and who's actually setting the state to be anything? So we should do set state. Should make sure that we always use set state instead of assigning directly to M state. Okay, and then but who starts the process? Is it exec? I guess it's probably process, exec. I should probably know this. Okay, so here, when we exec a process, then we set the state to skip one scheduler pass, which just means that the scheduler will ignore it for one pass and then it will run. Okay, so we're not getting any farther, but let's have a looky at the scheduler. And we can say that runnable threads. What is that pointer? Is this pointer null? Because if it is, then we're not going to get very far. Where is the scheduler choices here? No, so it's not a null pointer. I guess we can just print out thread. Do we have any threads in the list? Why am I not seeing anything? Choices, runnable threads. Yeah, so there's no runnable threads. Well, that's... let's just figure out what's going on. Okay, so we would be appending it here. So if the old state was not runnable and the new state is runnable, thread set state old runnable runnability goes from U to U. Okay, is runnable state old state new state. Okay, so let's look at that. Very first time it gets called, it goes from 1 to 1. Well, that doesn't seem right. Oh, look at that! I'm such a stupid. See, I bet if you're watching this video now, you saw me make that mistake a long time ago and then just fricking around. Okay. There we go. That's more interesting. So, assertion that node is head. I guess because we are trying to remove it from, so we're transitioning from 0 to 1. So here, right? So I guess we're trying to remove from here, and that's not going to work because it's not in that list. So that's something that inline linked list is a bit bad at. He doesn't like it if you tell him to remove something that he doesn't contain. So just so that we can make progress, let's do something a bit ugly here in set state. We'll say if G non-runnable threads contains slow. See, it even the name warns you that it's slow. And then we'll do the same here. I mean, in this case, it should actually, we should be sure that it is in there, so we can actually assert that it's in there instead. Okay, so we are switching processes a lot. A whole lot. Okay, so something is moving. So let's cut down on the debug spam and see how far this thing actually gets. The runnability debug logging, we can also lose that. Well, it actually boots up. Very interesting. It is, I would say it's a little, there's definitely something not entirely right here, but what is it exactly? So that thing didn't behave the way I expected, for instance. But is that because of the scheduling change? Who knows? It does feel slow. I wonder if that's because of the contain slow. So let's try something different. Let's not assert that, because remove will assert for us anyway. And we can say that if old state is not valid, then we remove, because all the other states should be in there, I think, but I was wrong about that. Okay. Notice that tail. So it's pretty slow. We need to get rid of this. So what does remove actually do? I guess when we put them in a thread list, we could have them refer to the thread list so they know which thread list they're in. It would just be a pointer, it wouldn't be the end of the world. So let's just do that. We'll try that out and see how it feels. Okay, so thread list. Okay. And we'll add something like no, not const. Okay. And if thread list, if m thread list actually, then remove yourself. And then thread. Oops. This should definitely be some sort of abstraction around this, but right now we are just going to write it this way. Okay. Because I just want to see the mechanism working. I don't care about the abstraction right now. No tail. You don't like my remove call. Okay. Okay. Well, why don't you tell me about it? So here we are just moving the things around inside of that list. And G non-runnable threads, and it's only happening here. Move, so I guess in the thread destructor we can do something more like if m thread list remove this. See, that's slightly nicer. Okay, so what am I missing now? We're not allowed to remove at this address. This is probably the assertion failed address, but let's look here. So we're like before kernel symbols have been loaded. That's why the backtrace looks like this. So that's assertion failure. Scheduler yield. ID disk device wait for IRQ. Okay. So where the heck was this? 1921. That's the assertion failure. Oh. So we're in pick next. Basically at the top of pick next. is not tail? Wait. First thing that we do is assert that the CPU flags have interrupts disabled. And then we're hitting. This is weird. Okay, I don't know why it's ending up like this, but it just doesn't seem right. So anyway, let's just ignore what it's doing and realize that the only place that actually calls remove is set state. Okay, so we should check here that we actually ended up on a thread list afterwards. And also in thread cpp prepend. We have prepend here. I forgot to look for prepend. Ah, see? So that's why we're so slow, because we're in the finalizer doing something. Okay, let's see what finalizer's up to. So the finalizer is this tiny little process here that is created by init that periodically, or not periodically, like whenever a process dies, the finalizer task is woken up from his very special lurking state, and he's told, hey, go and run destructors on this thread or process because it's dead. So that's his job. But for some reason, he's running all the time. And maybe it's because we are here. So let's see what he's doing. So he's waking up repeatedly. And he calls finalize dying threads. So let's see, why is he waking up? Gfinalizer. The way he wakes up is that the scheduler has this special thing here that if there are any threads in the dying state, then it will check if the finalizer thread is in lurking state, and if so, just unblock him. So let's see if that's what's happening. We're just like repeatedly unblocking the finalizer. Yeah, okay. So we keep seeing this thread that's in the dying state. That's why we are ending up here. So it never progresses from dying to dead, which is the natural thing that's supposed to happen when the finalizer runs. And in the finalizer, the way that this should happen is that finalize dying threads should take the collect all the dying threads here, and let's see, for each in state, looking for non-runnable threads, right? So let's put something here like, or no, let's do it this way. Debug printf finalizer killing off d threads, dying threads size. Okay, so how many? How many do you think you're killing? 0. Yeah, that makes sense. So he doesn't find them. So probably this thing here doesn't actually find the threads for him. for each in-state dying. Oh, see, I made this stupid mistake again. Maybe you all knew about it. You freaking probably noticed. See, I would almost like to be able to program that way. It's such a typical mistake. If I would like to be able in C++ to say, you know, if state in, or like m state in, and then runnable running, or however, I don't know how it should work exactly, but like probably these. That would be pretty natural. I would like it. But I'm also just making excuses for screwing that up. So we're still sluggish. Guessing it's still a finalizer? No finalizer. That's interesting. And are we actually sluggish? Maybe I'm just imagining it because I find that when I'm recording, then usually everything's like slower because OBS is running in the background and like encoding video and everything. So it's definitely different from performance characteristics of like running without video recording. This doesn't seem sluggish. But it just took a moment to start up there. Seems fine. It's kind of neat. Okay, so, geez, what's a way to kind of quantify this? So let's see. So let's look in the scheduler. We have this thing called stopwatch, which we could try. So we can make a little stopwatch, say scheduler. And what this will do is that it will count the number of clock cycles spent while the object was alive and then print them out. So it shows up like this. Of course, there's a lot of numbers to make sense of. So let's see. So it uses the timestamp counter in the CPU. Maybe we could extract the data. Where's the diff? Okay. Okay, let's not get carried away here because I didn't want to do this for performance. I wanted to do this for design. And if I start measuring, I'm just going to go down that whole rabbit hole of trying to micro-optimize it. So that's not what I want now. Because I just wanted to bust this thing into two separate lists. And I feel like we've done that, but are we taking advantage of it everywhere? So let's see. So this one is for each non-runnable, which will only go through the non-runnable threads, and potentially unblock, which will promote them to the runnable thread list. So that's pretty cool. So let's see. Maybe we can print out here, like checking on the non-runnables. Threads size. I guess size is slow. Yeah. Let's call those like underscore slow so that I know that they're slow. Slow in this case meaning like O of n because it has to actually loop through the list to find out how many items are in there. And then the runnables. So then we'll find out how many of those are. So see, these are not big numbers, right? We got like 6, 3, but you know, it's gonna add up as we keep going, especially if I start doing some of the things that I have in mind, like starting to have separate threads for every Windows Server connection and things like that. So of course you can see that we get more of these the more things we open, and we have to check on fewer of them. Yeah, there's no point in trying to investigate the performance of this thing right now, but I think I am happy with the movement, with the direction that this is going. So let's get rid of the debug output that we added. I mean, at least this really loud one. Verify that it builds with this debug flags. Yep. Okay. Let's do a little bit of a patch review. So, in process for each thread, we now go through all the runnables and the non-runnables. That's fine. It's not fancy, but we're gonna do it that way for now. And then here in scheduler, the first improvement is that we now do for each non-runnable to check on all the blocked threads, and potentially dying or dead threads or whatever, but like everything that's not runnable we do in a separate pass. Then just fixing up the debug code, and then down here when we choose which one to run, then we only look through the runnable threads. So it's nicer. Okay, and then here we are adding the global thread table. Now that we don't have a single canonical list, and we have that canonical hash table instead. And then we make the thread constructor insert into the hash table and put ourselves in the non-runnable thread list at first. And actually this makes me think that set state. Yeah, I guess this is probably the way that it should work from now. I mean, I would like to factor this slightly differently maybe, so let's have something like linked list thread list for state. Okay, like this. Is runnable state. And that would work like that. We can even do this. And non-const cannot bind to a value of sorry about that. Okay. Then let's see. Oh, actually, we can do it this way actually, because then the code will read a bit more nicely. Thread list for thread list. And thread list is thread list for state. New state. And thread list is new thread list. Then return. Let's remove this. Then thread new thread list. Append this. Okay, so I think that would be a bit more sane. Try with this. Oh, I don't have my fire demo. I think this is a bit nicer because then we could add more thread lists in a more straightforward way. Oh shit, forgot to check that nothing is, I just want to do a quick double check here that nothing is like smoking the CPU. No, okay. Cool. So, what do we have? And where were we? I forget where I was in the review, so let's just see. So here we have the thread table, 2 separated thread lists, and the constructor, right, so in the constructor we added to the thread table and then put him in the non-runnable thread list. I was thinking of making a function to do this, but we don't have to do that right now. Okay, and then in the thread destructor, if we have a thread list, then we remove ourselves from it, and we always remove ourselves from the canonical thread table. Then we are just changing all of these like raw assignments to mstate into setState calls. And then in thread initialize, this is like initializing global state in the kernel. We are just creating these 2 linked lists. And then the all threads helper that will give you a vector of all the threads can now take advantage of the fact that we know the size of the thread table beforehand, so we don't have to potentially avoid some dynamic allocation in vector, which is nice. And then likewise the isThread helper that takes a void star and tells you if it's a pointer to a thread. It's now O of 1, which is cool. Okay. Then isRunnable state tells us if state belongs in the runnable threads list, and it's for running and runnable. Okay. Then when we look for the thread list for a state, this is all we check, just isRunnable state. Okay, so that's cool. And then when we set the state of a thread, we just assign it to mstate, figure out what's the appropriate thread list, and if that's already our thread list, then we do nothing. If we are on a thread list, then we remove ourselves from it, append ourselves to the new one, and then set that to be our thread list. Okay. Fine. And then, yeah, so that one becomes out of line. I didn't need this helper, but I can just leave it there. It doesn't matter so much. Yeah, so thread gains a back pointer to his thread list. I think that would be fine. Okay, so here are those declarations of those things. I don't know why they say extern. They don't need to say extern. Why do they say extern? Or wait, those are pointers. They do need to say extern. This is a function. Yeah, I was getting confused here. This is a function. That's why it doesn't say extern. Okay. And then the for each state iteration helper chooses the thread list based on the runnability state. So actually, this thing should probably use thread list for state. So let's move these up to thread. We'll put them like this. Also thread. And let's put these in thread. So up here. And then let's put these guys up here. Have to forward declare PRT. Okay, thread list for state. Because then we can just do for state. We don't need to do that whole thing. Okay. And here we don't know the state, so runnable. Where were we? Right, so we're almost there. Here is where we were, right? So now this function will just get the appropriate thread list and iterate over that, which is cool. And then for each living, it has to duplicate the code to check both lists. Okay. And then we have for each, we'll do both for each runnable and for each non-runnable. And I think that's fine. And does this still work? Yeah, it does. Okay. Looks pretty cool. I think this is cool. For each non-runnable looks good too. Yeah, I think we'll commit this. We'll say kernel. Factor the scheduling. Factor the scheduling, and it's breaking it into multiple lists. Two thread lists, one for runnable threads and one for threads. Threads its state is responsible for moving threads between the lists. Each thread also has a back pointer to the list it's currently in, or on, or in. Yeah. Okay. Cool. Yeah, so I think I'm gonna end it here. So this was a bit of a different video, doing some refactoring instead of just implementing some feature, but I hope you saw something interesting here. So I would like to thank you for watching and for coming back, and I will see you next time.